Okay, recording started. Very good. So this is the list of our lectures, and we have 3 to make. And let me now concentrate on assessment of human impact on water resources. I'm not sure about the last one. I will deliver for sure the next one, decision theory. The last one can be maybe substituted by something else, because I am thinking of, in view of how we worked together, I think this year we worked really well, apart from, okay, we had the crisis. But I think we worked really well this year in remote, and I think most of the merit is yours because you were really proactive, patient, and always present. So I'm not sure. Maybe that the last lecture is substituted by something that is a little bit more detailed and technical. We will see. So water intrusion is fine, but I think you could study it by yourself. It's not really something that it's difficult or particularly, particularly requiring my assistance. Let's see. Okay, now let's concentrate on the human impact on water resources. So I click here, and then we get to this page. Let me check if, yeah, there is also PowerPoint presentation, but I prefer to use the web pages in the other version. Let me get it. This is wider, and let me expand it. And let me make a premise first of all, which is also related to what Emiliana presented. And there is today the crisis of the pandemic, which is of course a global crisis, and there is, there are implications that also reflect on our sciences, on water resources management, hydrology, and geosciences in general. Geosciences are the group of the sciences that study the Earth system. The implications of the crisis are not direct implications. I think there is little to contribute for our disciplines in reducing, in the recovering from the pandemic. It's something that we still have to understand because, for instance, there are branches in hydrology and water resources management that study the waterborne diseases, which it's a very important issue, like diseases like cholera, for instance, that they are vehiculated by water. For C19, it's not yet clear whether water may have a role. I just read this morning a newspaper news that in France they found traces of the virus in non-drinking water. It means water in the rivers, which is something that we expected because, of course, it's a virus that can last for some time, even if not allocated into a living organism. It's not yet clear what is the duration of and the viral power of the virus after some time that it's out of a living organism. But of course, we expected that it may get diluted into the water. It's not yet clear how long can it last in the water, and I think it may be in any case neutralized by the water treatments. So I'm not really sure that this is a risk, even if now I wouldn't suggest to drink water that is not treated if there is the doubt that it could have got in touch with a contaminant like a virus. I don't think this is a real risk. The reason is that, of course, we don't drink water into the cities which is not treated. We don't drink water from the rivers which is not treated. We may drink water from springs in the mountains, but in the mountains, I don't think that the virus can survive along to the point that it lasts in water underground, etc. This is something that has to be still inspected, but my perception is that this is not a waterborne disease. Actually, until now, we don't have any proof that it can be transmitted by animals, and we didn't get any proof that it was transmitted by water. So I think, to go back to my initial reasoning, that the direct implication of geosciences, environmental sciences, in the management of this crisis, I stress direct implication. I think it looks like it is limited. But on the other hand, there are indirect implications which are important, and they are, in my opinion, even more important because there is the risk that we don't see them. So the fact that there are indirect implications in anything, in a crisis, the indirect implications sometimes they become important because we neglect them. We don't see them. And so I think there is indeed now to pay attention to what could be the indirect result of the pandemic on the management of natural resources, on the exploitation of natural resources. And one implication could be, for instance, the fact that we give low priority to threats, to risks that look not priority with respect to the pandemic. So, for instance, environmental pollution, climate change is another very good example. There is the risk that we now give low priority to the risks originated by climate change because we are concentrating resources, we are concentrating our scientific founding on the pandemic. And so it may happen, for instance, that we reduce our climate change mitigation policies because we concentrate the resources on other problems. There might be the risk that we expand fracking because it may become convenient in a situation where maybe that the market is impacted, maybe the price of the oil increases, and then fracking may become more convenient, and then we expand fracking. So I think the role of geosciences is to make clear that our role as expert in environmental sciences is to make clear what are the priorities that we have to pay attention to in this situation, because there is indeed the risk that the concern for risks that are not directly related to the pandemic goes down, and therefore we are not concerned anymore by climate change, by environmental protection, because we want to use the resources for another problem. And this makes the human impact assessment, what I'm going to talk today, even more important than in a normal situation. So we are reacting to the pandemic, this is fine, and we are setting up procedures and policies. We have to take into account their human impact. So there are actions on the market, there are economic policies that are being setting up by the countries in order to minimize the impact of the lockdown. This is fine, but let's consider the human impact. In this situation, I think it is extremely important to be careful, because in a normal situation we have people that are looking at it, and so we have the citizens and the whole population that is looking at it, and if they don't like something, they tell you. In this situation, maybe that people are looking to something else, and then the human impact is not given high priority. I'm not saying that we have to give the same priority that we had before to our problems. I understand that now the main priority is there, but at the same time, I think it is our duty to point out what could be risky implications and what could be side risks that may be originated by the pandemic. The problem is that when we talk about human impact assessment, it's a topic that is very difficult, to some extent controversial, but it's not controversy that concerns me. The problem is that human impact assessment is indeed a complex assessment. It implies the analysis of complex processes where there is a lot of uncertainty. And this is the main problem, which translates in the fact that we really don't have up to now technical guidelines for it. It looks like it is a simple question, like, okay, it's clear what can be the human impact. It's very clear what may be the result of air pollution. It may be, of course, the risk of death for millions of people. But on the other hand, it's not clear for an engineer how to minimize this risk. What are the effective policies? I mean, if you talk about risk of earthquakes or risk of flood, it is quite clear. It is quite clear what we have to do. We have manuals, technical guidelines, we have laws that tell us what we have to do. So the engineer can move within a perimeter that is very precisely and rigorously identified. When we talk about the effect of climate change, mitigation and adaptation to climate change, to give you an example, then the perimeter is not well identified and we don't have any technical suggestion, like what are the design procedures to be used under the impact of climate change. There is no technical indication. And therefore, I think on the one hand, the problem is difficult. On the other hand, I think it is our duty to try to give a contribution. And this is why I decided a couple of years ago to set up this lecture, which is still, I think, not very satisfactory. When I read it yesterday and today in the morning, I said, okay, but I need to put some more here because it's, and actually I put some more in the morning. So it changed just this morning. But it is still something that is not satisfactory, but I thought that it was important that I tried to set up something. So let me start then to describe this, and let's elaborate a procedure. And what is in this page is just the result of my reflections, of my thought. And please feel free to contribute and criticize, because I am myself not really sure. I gave recently several presentations on that in scientific conferences, in conferences to policymakers, and some people did not agree. And I got several suggestions, but still, this is something that it's under development. And you don't have to be surprised by that, because we are talking about problems that came to our attention in the past 10 years, 10, 15, or for some problems, if you talk about air pollution, is a bit more, river pollution is again a bit more, but still these are young problems for which we have reduced information because data collection started only recently, and they are problems affected by uncertainty, and when there is uncertainty there is debate and to some extent controversy. So you don't have to be surprised that this is a topic that is not easy, and it's not easy to teach it in engineering. Anyway, let's say human impact. I don't want to, there is a link to a Wikipedia page. This is very descriptive, and if you open it, you can just see a list, a descriptive list of impacts. Also, this page, I think it is just descriptive, and I think it is just most of the content you can get it by intuition. And there is one thing that I wanted to tell you. It's about, and it's included in my webpage, some consideration about the role of human overpopulation. Of course, the human impact is increased by the development of human population. You can see this graph here, and it's on Wikipedia. The current population is about 7 billions, but you see the increase that there has been in the recent past. And also there is a figure which I took from Wikipedia on my page. Let me just show you it. So you see the increase started, the dramatic increase after the Second World War. And there are projections, growth scenarios that you can see here. And of course, this is a driver. But I think we have to be very careful when we say that human population is a driver, because it's a driver, but it's also something that positive, because increase of human population means that the living conditions in the world are becoming better, and I think it is something that we cannot control, and here we get into very difficult and controversial problems. So if you look at the Wikipedia page that I have shown you before, and you go to the links that are therein reported, you may see that some prominent scientists have stated that the only solution is population control to this problem. I think this is a very risky debate, and it's a debate that it's eminently political. So I prefer not to discuss this, because the role of the engineer is not the role of proposing solution to overpopulation, and it's our role is just to find other solutions, technical solutions, to avoid the human impact. Also, as a final consideration on this, I just would like to say that if you look at the countries that are most responsible for human impact in terms of litter production, CO2 emissions, etc., these are the countries that are more densely populated. So this would imply in the imaginary of people that where there is more population, there is more impact, and therefore some people may conclude, for instance, that it's developing countries the problem. Actually, density is not the same as absolute number. So most of the litters and CO2 emissions are produced in the developed world, and therefore if one wanted to concentrate on population control shouldn't be applied in Africa, should be applied in Europe and the United States, and maybe China now. So I mean, it's not an easy problem. It's not so easy to say that it's low-income countries the problem. Actually, they are not the problem. They are many, but their density is low, and their production of litter and pollution is in absolute terms, it's less than the corresponding productions in the developed countries. So I mean, I don't think it is really our job to discuss this, and I prefer that we stay on the technical part, and we don't discuss about this. Is maybe something for sociologists and the social sciences in general. So let me go back to the descriptive approach to human impact. You see this figure here, which is clear, and I mean, the message that I want to give to you with this descriptive treatment is that it's intuitive to understand what is the effect of the human presence, but as engineers, as people that have to look at technical solution, we have to make sure that we got all of them with a balanced and objective view, because these are sensitive issues, and there is the tendency, sensitive because I mean human impact is impacting our life in a concerning way, and when an issue is sensitive, there is a natural tendency, a natural inclination of people to look at only at the negative impacts, and to look at the impacts that are more important, more effective on our everyday life. And this is, a conservative approach, but as professionals, we have to get a full overview. So if on the one hand, we are concerned by CO2 emissions, and we want renewable energy. On the other hand, we have to be aware that also renewable energy has an impact. Either if you choose wind energy, there is an impact on the visual, there is an impact in terms of noise, there is an impact on the reliability of the energy that you get. So there is a social impact because it's not an energy that is always available. If we want to push hydropower, we have to be fully aware that the dams have a huge environmental impact, which we all know. So it is extremely important that you get a full overview, and it's your role of engineer to explain to people what are all the impacts. And I think this is the underlying principle. So to get a comprehensive picture, because there are several feedbacks and we have to be aware of all the implications, and unfortunately some of the implications are not easy to estimate. For instance, think at the human impact of dams on at the impact of dams on groundwater. This is something that is really difficult to assess, because when you talk about groundwater you get into a subject that is extremely complex. So, I mean, we have to pay attention, because we have to start from a full and balanced overview. Okay, and here there are two figures. The second is done by me, which try to explain to you what are all the implications. And then let's skip world population. We already discussed of it. I forgot to make a break. If you agree, I would make a break now, 5 minutes. Okay, so let's take 5 minutes break. So here I am. Now, the human impact was already the subject of a relevant interest starting from the early 70s of the past century. And it's indeed a key element of the concept of integrated water resources management. And I think it is interesting to see how the concept of water resources management developed. It was let's say, first proposed in the early 70s of the past century, so about 50 years ago, when there was initially the awareness, people got the awareness that the massive construction of dams had an impact on the ecosystem of the rivers and on the water quality. And it was the massive construction of dams combined with river pollution. So there was a decrease of river flow, an increase of river pollution, which caused the increase of concentration of pollutants, and therefore it caused the raging concern for river water quality. It was river water quality which stimulated the birth of the concept of management of water resources. And then later on, the concept went well beyond the river water quality. It was extended to groundwater quality, and it was extended to quantitative management, not only management of water quality, but also management of water quantity. And the concerns related to water quantity raised in the 80s, so about 10 years later, when it was clear that the increasing demands and the decrease in water resources availability could originate some problems in terms of sustainability. And therefore, at the beginning of the 90s, it was proposed a new concept which was called integrated water resources management. And integrated means that you have to consider water resources management in the widest sense, not only water quality, not only water quantity, but it needs to be extended to by considering all the implications of the use of water by humans, and therefore implications need to consider agriculture, so irrigation, and also industrial consumption, demographic expansion, and what determines the water demand. So there was a transition between considering water as basically uh, as as a resource and only as a resource, and we transitioned to considering water as an essential driver of our societal development and economy. So water resources management became more interdisciplinary. It was not only a problem for engineers, not anymore a problem for only engineers, only for environmental scientists, but water resources management became interdisciplinary. And this is why they said integrated. And at that time, therefore, several techniques were proposed in order to estimate how to best manage water resources and therefore estimate human impact. And the usual way that was chosen was to consider humans as an external driver. So the scientific workflow was first to study the water cycle in pristine conditions. And then once we gained a picture of water resources availability, water quality in pristine condition, then they injected the humans, and in particular water demand, production of litters, water pollution, etc. They injected the human as an external driver of the pristine system, which was very wise, and it is what we basically do also today. What we do in general, for instance, we learned that we need to estimate a flow duration curve, and the flow duration curve is estimated by using historical data that may go back to 1900. So they refer not really to pristine condition, but they refer to conditions that were existent before the human impact that is today our reason of concern. So we want to get water from a river, fine. We first estimate water resources availability before the design that we want to make, and then on that flow duration curve we put our water withdrawal as an external driver in order to estimate what remains into the river. This is the approach that we learned to follow, which is sensible, it's not a problem. On the other hand, by considering the humans as an external driver, it gives only an incomplete picture, because actually humans and water resources are something that is intimately interconnected, we learned recently, and there are feedbacks that we cannot consider if we only picture the humans as an external driver. So what I wanted to say is that basically the science exists. It was devised, let's say it was formalized 30 years ago. Some of the techniques that allow us to estimate the human impact on water resources by considering the humans as an external driver were conceived well before, like if you consider the impact on water quantity of reservoirs, it was studied in the 19th century. So the theoretical foundation have been put in place by Ripoll in 1883, so more than about 150 years ago. So some of the foundations were already existent, and the science was formalized in 1993. So on the one hand, there is a clear technical setting, which is already there. On the other hand, there is to say that this technical setting did not address some of the questions. And these questions are those that we need to learn how to deal with. For instance, climate change in 1992 was not a reason of concern. And the techniques that we use for estimating human impact now don't take the climate change into account. And I want to refer again to the example of the flow duration curve. The flow duration curve is estimated by using historical data. And then I put there the water withdrawal that I want to design. Where is climate change? It's not there, it's not considered. So on the one hand, as I said, there is this technical setting. And on the other hand, we need to update it. And this is our key and challenging question. How to update this technical setting that we are learning in this course, flow duration curve, estimation of water resources. How can we update it in order to take into account recent concerns that came forward, which we need to take into account? And this is the question. We don't have to make a mistake. Usually when you have new concerns, there is an inclination of people to say what we did so far is wrong, we have to reject it and create something new. This is not the correct approach. A very pragmatic engineer doesn't reject what has been used successfully up to 20 years ago, 30 years ago. A pragmatic engineer raises another kind of question. How can I update it? And this is, I think, the mistake that we don't have to do. We don't have to reject techniques that have been used for designing dams successfully, I would say, because with few exceptions we can say that it was successful, the water resources management that we designed so far. So we don't have to reject these techniques, because if we reject them, then we lose some grounds. We have to try to update them. Keep in mind that also scientists have, some scientists have this inclination to reject the previous science. And this is the result of inherent attitude of scientists to question the state of the art, to question the status quo. And this is an essential ingredient of science. And on the other hand, we have to be careful, because in technical sciences like ours, if you reject techniques, before rejecting them, you have to have the solution ready. Otherwise, we run the risk of not resolving urgent problems. So it is fine that we update old techniques or we propose new techniques for dealing with new problems. On the other hand, let's be careful in rejecting what has been done before unless we have a better solution to the problem. And today, unfortunately, in environmental sciences, we sometimes see that solutions are rejected without proposing alternatives. And the result is that we don't do anything. And if you look at climate change, this is a clear example. What did we do so far to mitigate climate change? Probably nothing. And in most of the countries, nothing. And I think that one of the causes is precisely the fact that we don't have a solution, an agreed solution that is ready. So we have to be very careful, because when we don't converge to a solution, the problem is not solved. And in some cases, you know, it is something that it's extremely dangerous. So let's try to set the basis of a framework. Let's see whether we can agree on a framework for assessing human impact on water resources without rejecting what has been done before necessarily, I mean. And the framework that I would like to discuss with you is based on these 4 steps. And first of all, perceptual assessment of the drivers of human impact and their priority. This is what I mentioned to you before. we have to be aware, we have to picture, sorry, all the impacts related to our problem, and in a balanced way. I mean, and the first step is this perceptual assessment. Let's forget for now quantification, and now it's important to put on the table everything, and if possible to prioritize in a qualitative way, like it's more important climate change or it's more important land use change. Let's try to understand in words, not yet quantitatively, what is the priority of these drivers. Okay, now we need to agree on the identification of objective and robust methods for assessing the effect of each driver. So we are making a step forward. Like, let's try to gain a quantitative assessment. So what is the influence? What is the weight of climate change with respect to land use change? Let's try to put numbers here. Now, once that we identified the priorities, we need to develop future scenarios. And finally, and probably the most complicated step, try to come to an uncertainty assessment. Again, we are engineers, and we need to estimate uncertainty. Otherwise, there is no design, and otherwise, if we don't have an estimate of uncertainty, our job is not well done and we are exposed to risks. Okay, so let's focus on each of these steps. Perceptual assessment of the drivers. Now we get into something that is controversial and something on which the scientific community doesn't agree. What are the drivers? What is their estimated priority? Now, let's try to make a list, and this is what I suggest you also. I made this list, but I think it is important that you have also a look at the web and try to see what are the potential drivers related to your problem. I mean, usually when we deal with a very specific problem, which may be water quality, maybe water scarcity, maybe the problem is energy production. So what we need to understand is what are the impacts caused by our problem, and then try to give them a priority. So for identifying the impacts, I think it may be useful to move forward with different steps of identification. First, identify broad categories, and then look into the categories for subdivisions. And this is what is done here. So there is a first list which considers broad problem like climate change. Okay, very good. And here I put the specification human induced, but you may also consider something related to natural variability. You may say, to me, climate change is important, no matter of what is the cause of climate change. Now, another impact is given by the regulation of river flow and water storage in lakes. So, what is the impact? There is an impact on the ecology. Is it important? Let's try to agree if the ecology of the river is a matter of concern with respect to, for instance, the impact of damming on groundwater. Okay, so the regulation triggers a lot of sub-impacts. Let's in the next step define, identify all of them. River training, if we have a project to design that includes river training, here there is training is misspelled, I need to correct it, just 1 second, I take a note. Training misspelled. So river training, and river training is sometimes necessary. For instance, if you want to build a barrage for water withdrawal, this is part of river training, and it requires further training to protect downstream from erosion, etc. In some places we have river diversions, which are put in place in order to produce hydropower. We have in some places river tunneling. River tunneling is frequently done in Italy. It's frequently done because we don't have much space for urban expansion, and therefore the solution is often river tunneling. But river tunneling has an impact on the flood risk. Freshwater withdrawal, if we design something related to groundwater pumping, getting water withdrawal from river, this is something that is impacting. Land use change, including agriculture, drainage, afforestation and deforestation, and irrigation and intensive agriculture. This, I put it this morning because it's becoming more and more a matter of concern. And keep in mind that there is a nice Wikipedia page on the impact of intensive intensive agriculture, which started after the Second World War. And it was stimulated, intensive agriculture, by the need of increasing food production due to the increase in the human population. And this development of intensive agriculture had a substantial impact. Today we are concerned by climate change, and we know that the production of meat, farming, and it's one of the main reasons, the main drivers of CO2 emissions. But if we change our diet by reducing meat consumptions, we have to be aware that then we need to further push forward intensive agriculture, which is impacting as well. So, I mean, these feedbacks are those that we have to really understand. Now, this identification of impacts, which you can expand the list, these are the broad categories. It is suggested today that it's carried out by discussing with stakeholders, and indeed the emerging concept in environmental management is that stakeholders' involvement is a necessary step. And so this is a first reason for discussion. And then what it's needed is to identify, to go into the detail, again with the stakeholder consultation, and distinguish, try to make a difference between them, between hard and soft facts. So let me better explain. We need to identify priorities. We have to identify all the impacts and give them a priority in order to understand what is the most important, what is the less important. When you have to make categories within a decision that involves a lot of stakeholders, the suggestion is to split the decision in different steps. So if you have a list of impacts and want to give a priority, the best solution is first to categorize these impacts in only two categories, because in this way you simplify the discussion. So this is why here I suggest let's focus on hard and soft facts. Let's make this split and see whether we can reach an agreement between people. You can pool the people with a vote. You can decide to use another criteria, but of course, even if you decided for a vote, it's much easier to vote between two alternatives than voting between 10 alternatives, because of course then if you split the vote, the decision is less robust. So this is an extended list of the impacts that you may want to consider. It's derived by expanding in subcategories what I mentioned before. Let's try to divide them in hard and soft facts. It is not easy. Let's suppose that you have to design a dam. So what are the impacts that can be considered to be hard facts? Some of them are not applicable, but for instance, it's groundwater impact. Downstream groundwater impact is an hard fact, or can we say that it's a soft fact? It depends on the status of the system. It depends on the status of groundwater. River ecology is an hard fact or is a soft fact? It depends on the use that you make of the river downstream. It may be that even if you build a dam, you don't have a strong reduction of the river flow. Maybe that the strong reduction is concentrated only in one season. So let's see if in that season we have to sustain important processes for river ecology rather than not. So it's extremely important to get priorities, and I think it is a good advice to start with only two categories. You may decide to use a decision support system, and we will discuss them later. This is a very useful way of categorizing, of taking decisions. And it is useful because the decision support system usually provides a visual perspective. And a picture is, as I mentioned to you already, it's more effective than a table to provide information. People may realize in an easier way with a picture rather than a table. And there are several decision support systems that will be used. We will focus on the theory of one possible approach. Here there is the link to open source decision support system, which is used by the United States Geological Survey for studying river quality. And keep in mind, very often the decision support system is just a modeling software. So if you have, for instance, a software that is able to predict what is the level of contaminant that you will have downstream a dam that is being designed, this software, if it is organized in a way to present the result in a transparent setting, in a rigorous setting, it's a program, it's already per se, maybe already per se a decision support system. And what is the essential requirement of a decision support system? Precisely the fact that the results have to be presented in a clear and transparent way in order to also give to you the required convincing power. But if your program is more than simply a code, it's a program that produces graphs in the output, and these graphs were conceived to be very transparent, very rigorous and clear, then your program may already become a decision support system. The decision support system also very frequently uses an object-oriented programming. So the various pieces of your model are represented in a picture as objects in a way that people can clearly understand how your code algorithm is structured. Now, once we identified and subdivided in categories and I suggest to start only with 2 categories. These drivers of human impact. Then we come to assigning priorities. Again, this is another task where decision support systems are very useful. And in particular, when you have a set of categories of human impact in this case. So you have a set of possible drivers of human impact. There are several analytical processes that you can follow to give weights to them. This is what we want to achieve in this step. We want to weight each region of human impact. And this is, you may say, why should I give weights? I could consider them prioritary at the same level. I can consider them at the same level of priority. Actually, in some cases, this may be possible. It may be possible that you find a technical solution that resolves all the concerns of human impact. But very frequently, this is not possible. Very frequently, you don't have a technical solution that brings the human impact to 0. And therefore, you have to choose a solution that reduces some impacts, but other impacts may not be reduced. And this is the reason why you want to give priority. Because if your priority is to minimize the CO2 emissions, then you have to choose a solution that gives priority to minimizing the CO2 emissions. If your priority is instead preserving the ecosystem downstream of a dam, you will increase the river flow downstream, but in doing so you produce less electricity, and therefore you increase the CO2 emissions because you need to produce electricity with another method. So assigning priorities is essential because you have to find a compromise solution. Again, avoiding human impact in general is not possible. We are here. We are impacting the Earth for the simple fact that we are here. If you want to increase our societal wellness, our societal welfare, we need to design solutions, and these solutions have an impact, which is unavoidable. Our task is to minimize this impact. And in order to minimize it, we have to know what are the priority impacts. And we may end up with a decision which we don't like, because, as I said, you have a consortium of stakeholders. Each stakeholder has their priority. And it's impossible to satisfy all of them, because people living upstream a dam have a different priority than people living downstream, and they are all reasonable. I mean, there is no question on that. The problem is to find an agreement and to find the best compromise solution, which means that in general the solution is not liked by any single person. Any single person dislikes it for some reason, and therefore, I mean, the decision is something that it's not easily accepted, and this is precisely the reason why we need a rigorous approach. Now, assigning priority, as I said, there are several analytic processes, and here I am linking the analytic hierarchy process, which has been used in a wide range of problems. We will dedicate to this technique a lecture, I think maybe Thursday already, and therefore we don't get into any more details this time. It's just a process that allows you to put together individual opinions and to find, with an analytic process, which means an algorithmic process, the best compromise solution. which is of course conditioned by the assumptions of the method. And we will see it in detail. At the end of the story, you come up with weights assigned to each driver. What are the weights? The definition of weights is they are numbers comprised in the range 0, 1, so that if you have a set of alternatives, the sum of the weights for each alternative is 1. So this is our definition of weights. They quantify, as I said, the importance of each category that you want to classify between 0 and 1, and the sum of all the weights is 1. Okay, and then let's forget for now about the analytic hierarchy process. Let's just understand that there are processes, mathematical processes, that can help us to reach the best compromise solution. Now, in order to help us to determine these weights, we often need to assess the effect of each driver, which is not easy because, let me make a practical example. Again, the construction of a dam. Let's suppose that we have to assess, give a priority, no, to assess the effect on groundwater downstream. And to assess the effect, we need to give a priority, so we have to determine the weight. So what is the weight that I give to the impact of the dam to groundwater? Maybe negligible, maybe very important. What weight should I give? A necessary condition is to quantify the impact. So to say something like, if you build a dam, your groundwater table downstream is not affected, or is affected in terms of a decrease of level of 2 meters on average, or it is affected in summer but not in winter. And this is not, it's different with respect to giving a priority. Giving a priority is to compare this effect with the other effects. But in order to be able to make a comparison, here is another fundamental role of the engineer, quantification of the effects. So what is the effect in terms of groundwater table? What is the effect of climate change on river quantity? And here it comes another essential task of an engineer, and this is something that I want to discuss with you after making clear that it's a different story with respect to giving priority. It's an essential step in order to be able to give priority. I suggest that we make our long break now, 15 minutes. Do you have any question so far?
Yeah. Can you please repeat again the difference between hard and soft facts?
Yes, so first of all, let's suppose that you have, let's start from the beginning. You have to to design an intervention like water withdrawal, okay? And water withdrawal, I said, like with a barrage, let's forget about the example of dam for now, just a water withdrawal. So first step, you have to get a picture of all the impacts. So an example may be, I make just a partial list. Noise. So noise is something that some people are much concerned because if you put a turbine there is a noise. Okay, this is a first example. River ecology. Another thing that people are much concerned of, because if they like fishing, they want to preserve the river ecology. If they like bathing, they want to preserve the river ecology. Another impact, it's decreased river flow downstream, which means less tourism, so commercial impact. Another impact may be water table levels downstream. Another impact, flag the risk upstream. Okay, you have to get a picture of all of them. And then at the end of the story, you have to end up with weights, like to the flood risk upstream, I give a weight of 0.05 because there is only one house and it's not a problem, because if I realize that it's a risk, I delocate the people. So the weight is low. How can I get to the weight? First, I have to give to agree what is the importance in words of each one of them. So I suggest you to split the decision in 2 steps. First, you agree with people, this is more important, this is less important, and then you get a first categorization, a first ranking, like the most important is climate change. The second important is the noise. The third important is, and then when you get an idea of a first list, then you pass to the quantitative assignment of weights with an analytic process. But within the analytic process is, as we will see, extremely important that you have a priority perception of what is more important and what is less important. In order to get to this perception, I suggest to split the decision in 2 phases. A first phase, 2 categories, more important, less important. And then you go into each category, the category of the hard facts. I say hard because you can reach a general agreement that they are important. And so you look at the category of the hard facts and you make a ranking without it. So the concept is splitting a complicated decision in subsequent steps of easier decisions. So the distinction between hard and soft is just a first decision. And I found it very useful because in some cases, there were people claiming that the impact of a dam was the main impact was downstream flood risk, and other people said another impact is the fact that there is local climate change, because a dam means increased evaporation and then down upstream and reduced evaporation downstream. So these people were concerned by local climate change. And then we came to a first agreement that indeed flood risk was an hard fact. You build a dam, it's clear that you have a flood risk upstream and downstream. Local climate change, we agreed that it's not really an hard fact, because local evaporation, local change in evaporation cannot have an influence on climate that is comparable to the impact of flood risk. I hope this helps to clarify.
It does. And just a follow-up question, the analytical hierarchy process would come in after you have identified hard and soft facts, or already to establish what is hard and soft?
No, in principle you can use it also for any kind of classification. But what I am suggesting is that the analytic process comes later with respect to a preliminary agreement in words of a preliminary ranking. And I tell you why, because as we will see, the analytic hierarchy process is based on comparing the drivers 2 by 2, like what is more important, climate change or flood risk, 2 by 2, because if you compare 2 by 2, it's easier. And then you just say it's more important flood risk, okay? And then what is more important, flood risk or river ecology? And you say it's river ecology, okay? And then at the next one. Now, when you make this comparison 2 by 2, I realize that it helps a lot if you had a preliminary agreement on what is more important and what is less important. Because by looking at the whole picture, because otherwise the comparison may look inconsistent. And we will see that this comparison 2 by 2 may end up with an inconsistent result, because you may say that climate change is more important than is less important than flood risk. Flood risk is less important than groundwater impact. And you may say that groundwater impact is less important than climate change. This is not consistent. And in order to make your comparison overall consistent, and we will see next week or on Thursday how to reach consistency, it helps a lot if you had a preliminary agreement on what is a ranking that it's not disagreed by your audience. Let me see. I need to click on the link, just 1 second. Condorcet paradox, let me see. I'm reading, I didn't know this. Yeah. Yeah. This is the inconsistency I mentioned, yes. And I think so, yes, it's cardinal rating, yes. This is what I wanted to mention. I think it is, and then there is a two-stage voting process, yeah. I think it may be useful to link this. Thank you for the hint. Okay, so let's take 15 minutes from now. Okay, here I am. Let me share the screen. Okay, good. Now, so as I said, we are talking now of models that allow us to understand the effect of each driver, and understanding the effect, as I mentioned, is important in order to give a priority to the driver and ultimately to assign a weight. And here I am making the example of historical data analysis because it's a relevant example, I think, but it's not the only model that we can use to estimate the impact of a driver. Historical data analysis is useful in order to understand, for instance, the possible impact of climate change. So if you have a project that is aimed to mitigate the impact of climate change, you need a prediction of climate change for the future. And this may be obtained, we already discussed this, in a deductive or inductive approach. Deductive means a model, a climate model that gives you a projection. Inductive means precisely historical data analysis. So this is why I make this example here. But as I said, it's not the only one. If you are talking about impact of dam on river ecology downstream, you need an ecologic model. If you talk about impact of a dam on flood risk, you need an hydraulic model. So in general, keep in mind that for each driver of human impact, you need to give a priority. And in order to give a priority, in most of the cases, you need a model, a method to quantify the impact. And this is another essential step. Actually, in most of the cases, this step is not controversial. For instance, if you talk about river diversion, the model is very simple. You just subtract the flow that is diverted by the original river. And this is not controversial. If you talk about flood risk, usually the hydraulic model is not controversial. People usually don't question the result from an hydraulic model, even if they could in principle, because there is uncertainty even in that case. But usually this is not the case. When you talk about climate change, indeed the model is subjected to controversy, and this is why I am making the example here of historical data analysis. And I am also making this example because it is historical data analysis, it is the approach that it's most frequently followed in engineering when you want to make a prediction for the future. And it's frequently based on linear regression. So I decided to focus on this example of historical data analysis, which means time series analysis. And time series, the definition of a time series is a sequence of observations in time. And linear regression, it's often chosen because it's very robust, which doesn't mean that uncertainty is reduced. It means that robustness means that uncertainty is never large. So there could be other methods with respect to linear regression, like exponential regression, that in some cases lead to a reduced uncertainty, but in other cases may lead to very huge errors. So a method of this kind is said to be non-robust. Robust means that, as I said, you never have large errors. So linear regression is often chosen for this reason. And linear regression may be analysis of historical data in general, a way in which we adjust techniques for engineering design to account for climate change. So we have a technique for engineering design that is based, for instance, on estimation of flow duration curve. You have an assumption of stationarity behind it. We discussed this when we studied the flow duration curves. Then we know that under climate change, the climate is non-stationary, so river flow is non-stationary, and you correct your flow duration curve through linear regression of some statistics, like the flow corresponding to a given duration is corrected by looking at its progress in time. Linear regression is something that you already studied in some other courses in your background, so this is just a reminder. On the other hand, keep in mind that this is something that it's really important. When you talk about something that is non-stationary in time, non-stationary means that it's changing in time, the statistics are changing in time. When you talk about something like that, it's linear regression is the simpler model that you can use. You get some historical data, you look at the progress of this data during the history, and if you see that there is a change, you try to fit this change with linear regression. So now let's look at the essence of linear regression. As I said, it's a reminder. And first of all, let's keep in mind that I may ask this at the exam, not as a first question, but as a very short question. It can be the subject of a question. And again, I remind you that I'll make a list of the most used question that I make at the exam. Now, linear regression, it's based on fitting a linear function to the data. Okay, so what is a linear function? And this is something that you need to keep in mind. It's not explicitly described here. Let me take a note because I want to update this page by describing what is a linear function. And a linear function, very simply, let me open another web page. Linear function. I can say this in words, but I prefer to refer to Wikipedia because so you have something written down. Just let me see if there is. Okay, here it is. This is a definition of a linear function. It is called here linear map. Doesn't matter, it's just a matter of terminology. So let's suppose that you have a function f which is linear. Linear means that, first of all, if you look at a graph, linear means that if you look at a graph, don't look at the graph here on the right. This is not an example of a linear function. It's placed here for another reason. If you look at the graph, it is a straight line. So this is a very coarse definition. The analytical definition is written here, and I am selecting. There are two conditions that have to be satisfied by a linear function f. The first is that fx plus y is equal to fx plus fy. This is also an expression of the superimposition principle, which we know very well in engineering. Okay, so the fact that fx plus y is equal to fx plus fy, it's the superimposition principle. And then there is the second condition, fax is equal to afx. Okay. Now, keep in mind that most, if not all, environmental processes are not represented by linear functions. Most of them are, if not all, are non-linear. The reason why we consider fitting a linear function is precisely the fact that it is more robust with respect to a non-linear function. Now, it's clear that if we adopt a linear function to represent an environmental process of whatever kind, we are not considering possible non-linear effects like tipping points. Tipping points are a clear example of non-linearity. And also, let me just take a graphic window. Give me 1 second. Okay. Sorry, I don't like this color here, so give me 1 second. Okay, now good. No. Just 1 second. Okay, very good. So let's get a graph of the function here, and let me see if, okay. Let me increase the size. Okay. So this is a graph, this is x and this is y. So this is x and this is y. Okay, so if you depict a linear function here, I am writing with the mouse, so be patient. If you depict a linear function here, this is an example. Just 1 second, I change the color. This is clearly a linear function. Okay, this is an expression of a linear function. If you have something like this, let me now make. This is not a linear function. This is a piecewise linear. If you make your own assessment of the two conditions that I mentioned before for the first line, this one, the red one, and you make an assessment of the same conditions for the blue line, you clearly see that for the red line they are satisfied, for the blue line no. This is called again piecewise linear. Now if you have a threshold effect, it is precisely this one in the blue line. And what is the threshold? The threshold is here. When you behind this point, this is my threshold, behind when you have a change of the slope, this is a threshold effect, which means that above a given threshold, you have a different expression of the linear function. And this is a threshold, and this is a tipping point. You can define it as a tipping point. Or a tipping point may be, for a linear function, something where you pass from a given state. Let me take another color. Like this one, sorry, 1 second, this one. Okay. You may pass from a given state. No, this is not visible. Just give me 1 second. Let me go to red again. You may pass from a given state of oscillating function like this, and at a certain point you get down to another state. So you have a change of the mean here. I had first a mean like this, and then a mean like this. Okay, this is a change of mean, which is maybe given by a tipping point. So these effects are not considered. When you fit a linear regression, you are referring to a straight line like the red line that is placed above the others. Okay, keep it in mind because it's extremely important. So now go back to our linear regression. The linear regression relies on the use of a linear function which has a form like the one that you see here. Yt is equal to a plus bt, and this is the linear part of it. Okay, this is the linear part. This is the analytical representation of a straight line with intercept a and slope b. Now, what is the epsilon here? The epsilon is an error or residual of the regression which we introduce because our data yt don't precisely fit a straight line, and therefore we need to introduce this additive error in order to fit the data. And the best the regression is, so the more precise is the fitting of the regression, the more reduced is epsilon. So a large epsilon means that the regression is not fitting the data well. A small epsilon means that we have a good fit, and therefore we estimate the two parameters of the regression, A and B. We estimate them by minimizing epsilon. And usually we use the least square approach, which is something that we already know. Perfect. This is least squares. Very good. Now, let me introduce the concept of confidence band, which is extremely important, that we can estimate for the two parameters A and B the confidence band. What is the confidence band? In poor words, but also in technical words, the confidence bands reflects our confidence in the estimate. The larger the confidence band, the larger the uncertainty we have on the estimate. Our estimates are estimates for A and B in this case. The two parameters of the linear regression models are A and B. The larger the confidence band for A and B, the larger the uncertainty in their estimation. Conversely, the lower the width of the confidence band, and the lower is the uncertainty in the estimation. Okay, now how can we define in rigorous terms the confidence band? Now, the confidence band, it's an interval. In fact, the confidence band can be also called confidence interval. They are synonym. Okay, now let's focus on this definition here. How frequently the estimated confidence band contains the true parameter. Remember, we have to estimate a parameter value which has a true value, and the confidence band in principle should encompass the true value, but of course it may also happen that sometimes it doesn't encompass it. We hope that the confidence band encompasses the true value most of the times we repeat this experiment. So now let's say that how frequently, I am reading again where I have selected, how frequently the estimated confidence band contains the true parameter if the experiment is repeated on different data, different time series. So this frequency is called the confidence level. So the confidence band is estimated for a confidence level. Typically, we talk about 95% confidence band, which implicitly means that the confidence level is 95%. What is this 95%? Is the frequency the estimated confidence band contains the true value. So you may then realize that the larger the confidence level, the larger the confidence band. If I say that I want to estimate a confidence band at 50% confidence level, it means that the confidence band is not very wide because it contains the true parameter only 50% of the times. If we move to a confidence band to a 95% confidence level, it must be larger because it has to contain the true value 95% of the time. Now, this concept of confidence band of a parameter for a given confidence level is something that is a bit nasty to learn, but it's something that you have to learn because it is extremely important for any engineering assessment and in particular for estimating the human impact. You will have to talk with your stakeholders about your confidence band. If you want to estimate uncertainty, you have to refer to the confidence band and the confidence level, and you have to be able to explain this concept in a very clear manner. So this is why I kindly ask you to learn these definitions, because also a good reason is that I may ask them. Okay, and then please have a look at the following para. More generally, given the availability of hypothesis testing procedure that can test the null hypothesis B equal to 0. So why we are interested in estimating if B is equal to 0? Remember, B is the slope of my regression line. In assessment of climate change impacts, very often we want to know if the slope of the regression line is 0 or not. Because if the slope is an increasing slope, it means that you have an increasing in time value of the variables. If the slope is declining, you have a decline in time. And if the slope is 0, you have stationarity. Okay, so we are interested in testing if the slope can be assumed to be 0. And now we say in statistical terminology that this is our null hypothesis. My null hypothesis is B equal to 0. I want to know whether I can accept this hypothesis or I have to reject it. The alternative to the null hypothesis is that B is different from 0, and then a confidence interval needs to be estimated for B, and we see if this confidence interval includes 0. if it includes 0, I cannot reject the null hypothesis. A bit complicated to say, but it's just a matter of understanding the terminology. It's complicated to say, but not really complicated as a concept. Now, keep in mind that also we need to define, there is one thing that I didn't define so far, and it is here the confidence level is often expressed in terms of confidence level y, which I said 95%. It is expressed in this term 1 minus alpha. So if I say 95%, which means 0.95, I can also say that this is equal to 1 minus 0.05. What is the complement to 1 of the confidence level? It's alpha, which is called significance level. This is a terminology used in statistics, and please learn it, because you may be asked not what is the confidence level of your confidence band, but people may ask you what is the significance level. And you have to know that if the confidence level is 95%, the significance level is 5% or 0.05 if you prefer to speak in percentage or in relative terms. Okay, now, as I said, in linear regression, we are interested in computing the confidence band of the parameters, and in particular B, and there are procedures for computing it. We don't go into the details. If you use R for computing the linear regression, it's very easy. There is a function in R to compute the linear regression, and the same function gives to you the confidence intervals. Now, the computation of the confidence interval is affected by assumptions that are made on epsilon. And in particular, these epsilon, which are errors or residuals, they are not synonyms, but you may heard about errors and residuals. From an engineering point of view, roughly speaking, you may consider them synonyms. These errors are assumed to follow a normal distribution. I'm sure that you know what a normal distribution is. We already also said something. And they are assumed to be uncorrelated. Okay, so keep in mind that in hydrology, usually these assumptions are not satisfied, and therefore it means that the confidence bands that are given by R may be approximated. This is something that you have to know. And the larger is the departure from independency or lack of correlation, the larger is the departure from Gaussianity, normal distribution, the larger is the approximation in the computation of the confidence bands. We know that uncertainty estimation is affected in itself by uncertainty. This is something that we have to know, and of course we have to try to get a comprehensive picture of the reliability of our estimate. Okay, and keep in mind that something we already discussed, the presence of correlation widens the width of the confidence interval. If you have Hurst-Kolmogorov cycles, this is correlation and widens the width of the confidence interval. Okay. So keep in mind that if you assume that the data are uncorrelated and in it you have instead the presence of Hurst-Kolmogorov effect, confidence interval is widened. We have to be fully aware of the variability of our estimates. Here you can see again the two figures that I already proposed to you. Linear regression on a 50-year-long sequence of annual maxima, and below it there is the corresponding graph of the annual minima of the Po River, and you see that the regression line is highly variable. What does it mean? It means that the confidence interval of the estimate is large. So in this case probably includes for the B parameter the 0, and here is the minimum. Okay, what is this? This is an example again of a model that is is conceived for estimating, quantifying the impact of a driver. When I introduced this example, I said there are other models that you can use, not necessarily historical data analysis you should use. You can use models. Perfect. And now there is a section dedicated to models. And it's not detailed because models can be very, very different, very diverse. They can be hydraulic models. They can be like groundwater models, different kind of models. There is to say that these models in some way should be coupled with the human presence, because if you want to estimate the impact of a driver, of course the impact on humans or human impact, if you want to estimate it, you have to introduce in some way in your model the presence of humans. For instance, if you use a hydraulic model to estimate flood risk, at a certain point you will have to compare your results with the presence of houses. So if you get an estimate of a flooded area, then you look for houses there. And this is the time when you couple your hydraulic model with the presence of humans. Or if you use a groundwater model to estimate the impact of a dam on groundwater dynamics, at a certain point you will have to compare the groundwater dynamics resulting after the dam with the water withdrawals. And you may conclude that the changed groundwater dynamics doesn't allow you to satisfy the water demands. So at a certain point, you introduced water demands in order to quantify the impact on society of the dam. So there is a certain point when you need to introduce the societal component. And again, the societal component may be an external part of the model, like when I look for houses in a floodplain. This is not part of my hydraulic model. It's something that is introduced as an external information. And so you get the first category, methods representing the human impact as an external forcing, an external information. On the other hand, there is today a large part of the literature that says this is not enough. This solution is not enough. We have to devise a model that embeds humans as an inherent component. In this case of the hydrological cycle, because I am estimating water resources availability. And let me give you an example. Again, referring to the very simple example of the flood model. You may consider the presence of an house as an external information, fine. But what may happen in reality is a different story. So you applied your hydraulic model by ignoring the presence of the house, and therefore you ended up with an estimated flooded area. But in the flooded area there is an house. So what may happen is that people living there, they build a levee around the house to protect themselves. This levee, and this is what actually happens. If you look at the floodplains of the Po River, people living there, they build levees, and they are to some extent allowed to do that. But if you don't consider these levees in your hydraulic model, then your estimate of the flooded area is not correct. And it's not correct because you didn't consider humans as an inherent component of your model. So now there is a growing awareness of the fact that environment and humans are tied by a two-way connections. It's not only human conditioning the environment, it's not only the environment conditioning humans, it's a mutual conditioning with feedbacks that go back and forth, and these feedbacks has to be considered. If you just consider humans as an external forcing, you don't consider this feedback. So there is the problem that if you use this second category of models, they are more complex and they involve more parameters and they are not robust then. And why are they more complex? Because if you want to embed the humans, you have to be able also to predict what is the human reaction to an environmental forcing. You have to predict, in the case of the house, that people build a levee. And predicting human behavior is not easy at all. We know that. And the social scientists tell us that it's indeed not an easy task. So, sorry, let me minimize this. This is not an easy task, and it means that the models become complicated. It means that uncertainty of the model may increase. So the model may end up with, in some situation, being more reliable with respect to a simpler model, but in some other situation may end up with a prediction that is completely unreliable, and so the model is not robust. The example that you find mentioned here of two ways connection is another example with respect to the one that I made, and I made it on purpose because it's useful that you see different examples. So, I mean, you have these two solutions in order to understand what could be the impact of humans, and of course it has to be carefully considered, and you don't have specific guidelines telling you what kind of approach to adopt in different situations. Okay, and now here there is a para on the development of future scenarios, and the problem with future scenarios, we already discussed it. If you draw several future scenarios, you can't get rid of uncertainty assessment. The collection of scenarios is not an uncertainty assessment. A collection of scenarios is simply a collection of different modeling responses, but each of them should be also associated to uncertainty assessment. Otherwise, I mean, the range of the scenarios by itself, it's not uncertainty assessment. And then, uncertainty assessment, it's indeed of a problem. We made the example of the linear regression. Once that we get the estimate of the confidence bands for the linear regression, indeed, they can be used to assess uncertainty of the linear regression. But this is a very lucky situation. If you use other models, like climate models, more complicated models, uncertainty assessment is a big open question, and which we already discussed, so I don't want to get into more details. I think at this stage you have an overview of a possible solution for assessing the human impact, and the possible solution relies on identifying the drivers of the impact, I quantify their impact through models, and finally giving a weight in agreement with your stakeholders to each driver. We still have to discuss how to elaborate the weights, and this is the subject of the next lecture. I think for today we can close here, and just to give you an overview of what is the future, I think on Thursday and maybe in the first part of Monday's lecture we will deal with weight estimation. And then I want to propose to you an exercise in R, which is not particularly complicated, which will be the last one. And I think in this way we get to Monday/Thursday next week. And then we have final 3 hours to discuss last issue, which may be, as I said, saltwater intrusion or something different. Okay, I'm willing to address your question, if any. Just let me de-share the screen, and then let me get to the, sorry, to the chat. I want to make sure that I'm not missing anything. Okay, please, if you have any question. I also would like, not now, but if you have any suggestion to improve this lecture would be great. Okay, let me see. 11 people still here. Very good. Okay, again, I think we can close here. I need to put the video on. I hope by today to get it done. Okay, students, thank you. See you on Thursday morning. Ciao.
Ciao.
Very good. Bye-bye.